Alright guys, so today we're going to talk about trigonometric substitution. So let's say we have an integral of the form, you have a function say of u. Let's say polynomial, probably just a power of u. And then you have something that looks like the square root of u squared minus 1, or a squared, let's say. Well, this is the type of integral that we would like to do a trigonometric substitution on. And how do we think about these substitutions? Well, we gotta go back to our Pythagorean theorem. That's where it all starts. So let's say we have a right triangle. That's a beautiful triangle, but bear with me. And then you're gonna have a hypotenuse C, and it's gonna have an opposite to this angle theta A and an adjacent B. We know from our Pythagorean theorem that c squared is going to be equal to a squared plus b squared. So now we go ahead and try to compare to what we have. And you say, okay, I have a square and another square, but I have a minus. That doesn't quite work because right here I have a plus. But you can always subtract a squared on both sides, and you get c squared is minus a squared rather, equals b squared. So now it's starting to look a lot more like it. What that tells you then is that you would need the first term, whenever you have a minus sign, the first term would correspond to your hypotenuse. So in our particular case, that hypotenuse would be u. And then we would have to pick where to put a. Kind of unfortunate. No, I chose a the same way on both. Wow, that's great. But unfortunate that I put a here in this triangle. That is unfortunate because really when you do that substitution, you would pick it to go here. And then by solving from the Pythagorean theorem, you get that this would be your u squared minus a squared. So that would be the generic substitution. Whenever you have some expression of this form with a square root of that form. It doesn't have to be in the denominator, actually, but I put it there. All right, so now let's say that you have an integral with yet another function, g of u, and then you have your square root of now a squared minus u squared. Now, I still have a minus, so I know the guy in front has got to be the hypotenuse. So that guy there would go here, the square root of it. And when you put it there, you usually will put your u here so you get a sign substitution. We're going to get into the details of that here in 1 second. But here then you would have a squared minus u squared. So this would be your generic triangle for this type of substitution. Lastly, you have the case where you get an integral of some function, and I should have had du here. It looked very ugly there, sorry about that. And let's say you have a function h of u. I'm going to put it in the denominator again. Let's say you have square root. It doesn't have to be a square root, but just because I'm putting this term here, that's why I'm using the square root. A squared plus u squared. Now you have a plus, so you're back to this situation. You don't have a minus, you have a plus. So we have a plus, then we're talking about that both sides are, one will be, or both terms rather, one will be an adjacent and the other will be an opposite. But the hypotenuse then will be just the square root of a squared plus u squared by the Pythagorean theorem yet again. And so here we normally pick u. Oh, it was a bug, huh? Like something is scratching, itching. Oh well. Premium content you get here. All right, so anyways, you put your variable here as the opposite of the angle theta, and the other one will be your adjacent. With that, what would the substitutions look like? Well, u over a would be, in this particular case, hypotenuse over adjacent, which is the reciprocal of adjacent over hypotenuse, which is a cosine. So the reciprocal of the cosine is the secant. So if you write it like that, you get u over a is equal to the secant of the angle. And that gives us the substitution u equals a secant of theta, from where we get that du would be a secant of theta tangent of theta d theta. And lastly, the square root of u squared minus a squared. This is opposite over adjacent, so u over, or this square root over a will be the tangent. Let's multiply a on both sides, and you get that square root can be substituted in with a tangent. So this would be a tangent. This would be a function of the a secant, and then the du would be substituted in with a secant tangent d theta. All right, our substitutions here would be u over a. Now in this case is opposite over hypotenuse. In that case then it's the sine. So we get u equals a sine, from where we get du being a cosine of theta d theta. And then last thing we do is just square root, in this case square root of a squared minus u squared over a. That would be adjacent over hypotenuse, and in that case is a cosine. So you just write that the square root of a squared minus u squared equals a cosine of theta. All right, and now lastly, for the tangent, u over a is opposite over adjacent. That's tangent. So u is a tangent of theta. And then du is going to be a secant squared d theta of theta d theta. And then your here you get square root of a squared plus u squared divided by a. That's going to be, again, hypotenuse over adjacent, that's secant. So when you just write the square root, multiplying times a on both sides, you get a times secant of theta. That's just the reciprocal of your cosine. So these are the generic substitutions we're going to be working with. So now let's move on to some examples. All right, so let's start with this one here. Notice that I have a minus, so that means the first guy is going to be my hypotenuse, or the square root of it rather. So in this particular case, my first term is going to be 1, so that goes there. No ambiguity, we know where it goes because there's a minus, so the first guy has got to be our hypotenuse. Then we have a choice. We can put our square root of this guy, which is 2x. We can put it here or here as an adjacent or an opposite, but traditionally we put it as an opposite, so you get a sign substitution. And then the Pythagorean theorem tells us that this guy right here would be 1 minus 4x squared. And then we get that opposite over hypotenuse, which is just going to be 2x, is going to be equal to the sine of the angle. And probably a little bit nicer to write x as 1/2 of the sine of the angle. From here we can take our derivative and get that dx is going to be equal to 1/2 of the cosine of the angle d theta, or theta d theta. And now we do this square root. That probably is too small. I'm writing a little bit small. So square root of 1 minus 4x squared over 1, that's going to be adjacent over hypotenuse. That's going to be a cosine. All right, so let's try to plug things in here. The dx, so let me grab a highlighter. Probably not green, that probably wouldn't work. Ugh, that's ugly. Let's use a different color. Let's just use a red pen. How about that? So the dx will be it's gonna give me a half of cosine of theta. I'll write it in red just to hurt your eyes, and also because, well, then we can identify it. All right, so now this term right here. Some people address this term a little bit differently. I don't like that, but some people would just write this as 1 minus and then plug it 4, and then plug in terms of x, they would plug in 1/2 of sine and then square it, do all the identities. I'd rather go here and notice that this term is just this guy cubed. So 1 minus 4x squared to the 3/2 is going to be cosine cubed, and I can just plug that directly into my integral. So I get cosine cubed, and I'm good to go, because then I can just operate this and go from there. Now, how would you do it if you don't want to do this little bit of trigonometry? Then you have to go ahead and substitute it in the value that we got for x here and plug it in. And then you have to do all the identities and all that. I find this really messy, my opinion, but some people like it, so that's why I'm showing you that you can do it that way. At the end of the day, you're still going to get the same thing we got, which is going to be your cosine of theta. Why? Because you see the square of the 1/2 will be 1/4, cancels the 4. You get 1 minus sine squared. Would be great if I just change this and put a cube here. That'd be awesome. So it cancels out and you get sine squared. 1 minus sine squared is cosine squared. Then you take the square root and cube it. You get the cosine cubed. So in this particular case, now we get 1/2 of the d theta over cosine squared of theta. Now that's the secant squared. If we write it as 1/2 secant square of theta d theta, and now you know that that integral is going to be equal to 1/2 of the tangent plus c. Let's separate this out. And this is going to be, what is the tangent? Well, it's going to be 2x over, so opposite over adjacent. That's the tangent, right, of the angle. So 2x over the root of 1 minus 4x squared plus c. And now just note that the 1/2 and the 2 cancel, and you get x over square root of 1 minus 4x squared plus c. And that's that. All right, so I thought I was going to have enough time to do 3 problems in one video, but the video is getting too long. So this is going to end part 1. So then I'm going to do part 2, where I'm going to do another 2 problems, because they apparently take longer than I expected. So in the meantime, you just get a doggy. Nah. Yeah, that's what you get. Terrible doggy. Oh well. All right, till next time.